Hello, hello. So today we started our day zero perception, and so we will be continuing with day one on the same day itself because we have been running out on a bit of time. So today it's a bit late. So we won't be going to much in this thing. We won't be taking too much of your time. So the thing is, for now, let's jump right straight into it. So now we have, yeah, in digital, we have to learn about the different types of like how our human eyes can fall into different types of like optical illusions, etc., etc. How the machine perceive things and all those things. Regarding so in this day one, we will be mainly focusing on how the machine will be able to read or understand or see an image. So before that, we will go towards like how does a machine or like how is an image generated? Like it's we can say like I'm pretty sure you guys are pretty much familiar with this pinhole camera. So pinhole camera can be said to be like one of the first things that has been invented that can like properly like display or display the scene onto a screen. So it even artists in during the like olden times used to have this chambers, dark chamber. They call it the dark chamber. This used to have tiny holes, and because of that, they would be able to trace out the scenes that are happening outside of the hole. So artists have been using this since ancient times. Uh, so coming to how an image this thing, we have talked about what is perception, how it is the machine's ability to interpret what is happening. And so before we go into like how an image is formed, we need to understand what is an image sensor. So image sensor, like it is a device. So it is a device which converts like the light wave. Like basically, you know how we see things is when the light from the sunlight or any other light sources reaches to an object and then it gets reflected off from it and it reaches our eye. Same case, instead of the retina, we have the sensor. So what this sensor does is it converts those light coming from reflected from the object and it converts them into electrical signals. And so previously used to have that the chemical film and for the Polaroid cameras, etc., etc. But as soon as we started going to the digital world, it has been shifted towards more of a sensor type, electrical sensor type. So it has drastically reduced the amount of time that is needed to uh, generate the image because previously in the film type cameras we have to dip them in this thing and like that there was a lengthy process before we could get our own camera, right? I mean on our own photos. And when you make a mistake, let's say you overexpose it, you underexpose the camera, like the sensor, and then it makes it like you cannot just change it. You can like a film wasted is that it's like it has been wasted. So we have come a long way from there. We have translated towards digital, and so coming to camera sensors. So what it does is you can see in this camera, you can see that here we have the camera sensor. The camera sensor will have this thing many tiny pixels. So it will have many pixels, and then these pixels, like let's say these are the pixels, like all this tiny box will be the pixel. They will be converted to the required voltage, and then they will be used to transmit this type of output. So coming to this, we have like what are this thing, the camera sensor basics. So we know that each sensor like it contains millions of light sensitive pixels. So they have tiny pixel like which are light sensitive, which can convert it. And so it depends, like the resolution depends on the size of the image and the size of the pixel, like size of the entire sensor and then the size of the pixel. And so coming to this, we have the different types of camera type, like what are different types of camera sensors. So they can be mainly divided into two types, CCD or charge coupled device, or CMOS, complementary metal oxide semiconductor. And so coming to the difference, CCD used to be popular before, but now it's like mainly like like currently the world works on CMOS mostly, and it's because of the advancement of like the digital electronics and all the in the semiconductor industry. So coming to the charge coupling device. So as you can see in the image here, each of this pixel will be converting the light coming to it to their corresponding value. But how it is transferred is that is the value of each pixels in this row or color will be shifted towards this lower area. So what will happen is like this can be a shifting mechanism where each of this pixel value will be coming one by one down, and it will be shifting towards the sensor, like the analog to digital converter. So we have an oscillator, which will oscillator, and then a timing generator, and then a clock cycle. It will generate at what instances the pixel values are transferred here, and then how it will be transferred. That's it. We don't have to go into too technical details here. And the thing about this is they were used like so, like the charge are transferred like one pixel at a time. Like so, it's a sequential way of transferring, and so it's a bit slower as compared to CMOS. So what happens is in CMOS, you will see that each of these pixels have their own circuit inside. Like the sensor has a different, like has their own individual circuit, which can individually convert each of these each of the light sources, light emitted to it, and it will be converting it, it will transmit. So it can be more of a independent and it can run in parallel. So this can be once this, let's say this converts it, it will transmit. Similarly, this you don't have to shift it downstairs like as you happen with the CCD. So as a result, CMOS type sensors are a bit faster, and so they are now widely used in digital cameras. But one drawback of CMOS is that the camera sensing area should be is lesser because you have to accommodate the circuit as well. But nowadays, because of how small we can make the circuit today, now it's becoming prevalent. It's becoming good. And so we have talked about different this thing. Now we'll be talking about sensor sizes. In sensor sizes, we have the image resolution. So image how the sensor size will affect the image resolution. So basically, we think like the larger the sensor, the higher the resolution. Why? Because also like if the sensor area is large, it can take in more light, more it so it can also perform in like lower light, like in a low light medium, like environment. Can work like that. And the angle of view can like it also depends on the size of the sensor, and it also like depth of field. Like these are some of the parameters that depends on the sensor size. So before we buy the camera, we have to know like these are the parameters, some of the parameters that makes us like choose what type of camera we have to buy. Then coming to this, we have let's say colors. So we have talked about how images are converted to well, like images are basically the light intensity which are converted into pixel values. But how does it record the color? So coming to that, that is why we introduce filters. So since they cannot read out like which specific color it is, we put in front of the sensor, we put filters. Let's say red filter, which makes it sensitive to red light and nothing else. And so similar to that, we can make the sensor be specific to that type of light instead. So coming to that sensor, we have this the one of the most common filter that people use is the Bayer filter. So in Bayer filter, you can see that uh, it the corresponding like the filters. You can see that it is red, and then it is green, and then it is green, and then it is blue. So each pixels, so the red pixel area will be sensitive to red, and then the green will be sensitive towards green, and the blue will be sensitive towards blue. So we know that one pixel is not getting the entire color range. We're getting basically one sensor will be getting like one pixel. One pixel will be getting one specific type of color. And based on the algorithm, on the software itself, it is basically it gets converted to like how what is the if the pixel is reading this image like this value of color of intensity this, then what will be the surrounding, what is the probability of the neighboring pixels to have this color, etc., etc. There are algorithms like this. We won't be going to that for this one because there is no need. Uh, so we can now we know that how the camera is being selectively towards a specific wavelength of light. And so now after we know how there are multiple like the colors, how colors are being perceived. Now we know look towards the color space. Like there are many color space. You need to know how like so different. Like we will be using different libraries. Mainly we'll be focusing on OpenCV. So we have to know what type of color spaces its library uses. And so before this thing, like RGB is for red, green, blue. BGR is for blue, green, red. HSI is for hue, saturation, intensity. And CMYK stands for, I've forgotten. I can't recall what this stands for, but it did stand for cyanide something. Cyanide, something. Yellow or some color scheme. So each one of them have their own different advantages. So we'll see how like different library utilizes them in a short while. So in color spaces. Now, how does a machine see an image? We see image in terms, we can see the boundaries. When we see an image, we can see the boundaries. We can see how the image has different colors, etc., etc. But how does a machine know? Like, how does it see? Actually, it sees in terms of pixels, like the pixel intensity in stored in an array. So typically, the value ranges from 0 till 255 because 8 bit. It depends on the bit size, basically. So 8 bit, for 8 bit, the value ranges from 0 till 255. For 16 bit, the value will be larger. So in this range, we have 0 till 255. So in before we continue to the next one, I would say again, in binary image. So 0 corresponds to black, no light whatsoever. 255 corresponds to white. It has so it is the highest intensity. And so what happens is when you, let's say when you're taking a camera, you're taking a pixel, when you overexpose it, so when you overexpose it, like the exposure time is large, then it becomes that more light will be allowed to enter the sensor. So what it does is it gives it more time for the sensor values to saturate. That's why you get bright images when you overexpose. Similarly, so in binary images, you will be learning about binary images in the next classes. But binary images basically means the color ranges from black and white. So black and white images. It is different from a grayscale image. A grayscale image basically has values ranging from 0 till 255. So it will be a gradation of gray color, basically. So a computer basically sees in a grayscale image. Like, well, how we are seeing is a grayscale image, but for them it's mostly like they don't see in terms of color. We see in many exercises, you'll see that you can divide an image, an RGB image, into three channels: red, green, blue channels. So when we take those out, we'll see that the red channel will be mainly red in color, like the images will be mainly red in color, but it is not how the computer will see. It mainly sees in the values of 0 to 255. So it's more mainly coding in, like, let's say in RGB. In RGB LED, we can code the amount of value, like let's say three channels. If I want it to be mainly red, then I can code the value to be 255 in the red channel, and the others I can make it to be 00. Similarly, how the display the image, like for us to see, is somewhat similar to that. But in reality, it's just seeing the grayscale events. So now that we have gotten that out of the way, we will now start this thing. We'll go for more like a coding approach as well. So let's go to VS Code. Yeah. So here I have this thing. I have a bunch of images that we won't be using them all. These were some. This will be used in your day 5 or day 6. I cannot recall. It's for fisheye to this conversion, fisheye to panorama conversion. So now let's go and make it. So let's say for this one, we will be trying to learn how the camera is. We will make the uh, this thing, the computer display what how it sees elements and how colors work basically. So let's name it this. And so for this, there are many libraries that you can use for loading and you like to do image analysis on an image. Basically, we will be focusing on tomorrow. Like many will be focusing on OpenCV, but there is also another library which we call as PIL or Python Imaging Library, if I recall correctly. And so now let's see. Like I have said that we need to know in what color space image is stored or analyzed by a certain library. So let's say we want to import OpenCV, and then let's say I'll name this image one, image one. Okay, so the image, so the image that we'll be analyzing now for now is this image. So we'll be analyzing this image. So this image is in RGB form. So now let us print out the image. For printing out, we would need, yeah. Then I will need to load it here. You see that this is totally different from the original image, right? Like the original image is this thing. Let me here. So it's totally different. It's like the so how in image storage we have the three channels, right? Blue, RGB, red, green, blue, and then but OpenCV reads in BGR, blue, green, red. So the order is different. That's why when it reconstructed the image, it is making it in this format. So we need to know what the library uses basically. So we can change it. We can change this to our specific, like, so since we know that we are changing this to like BGR, so we will be changing it to RGB. So for this one, mhm, let's say let's name the let's as I'll just name it as image one. And for this, you have to uh, CBT file. No, no, it's not CBT. It's simply color. Color. No, let me call. Like the thing is, you have to remember the syntax. So CBT 233. So since it is BCR, we'll be changing it to RGB, right? RGB, and then we will print the image. Uh, CV two and then RG. Okay. So it will be So let's display is one. Let's see. Okay. So now it has converted to the what do you say? The RGB, yeah, the RGB. That's so now there's this another library which we have. It's a Python library, so it's called yeah import. We have to import things. Then for the syntax for this is let's name it as image two. Image two. Then let's name it as um, um, shape. But the library in PIL, it uses the RGB format. That's why we didn't have to convert it as we had to convert it with OpenCV. Now, let us see how the machine will see elements, right? So, in order to see it, we would need to have this thing, the array, right? The array. So, let's name it as pixels. I think pixels are incorporate word. Thinking of things. It can work. Then what I need is image. Image. Two. Yeah. So let's do. Okay. Now let's. No, no, no. It is not. This it is. Okay. Yeah. Yeah. See. Now you see like this is how the image is stored. You can see that it has three channels: red, green, RGB. Yeah, red, green, blue. So this is the first pixel. Like this is the first pixel for row one, like here, and then this is the for second row, like around the next to the next, the first, like this thing, and then we'll go around, and then this will be the ending. So you can see this is this stands for G, and then B. So like let's test this out, right? Let's test this out. We have this pixel value. Let's test this out in say hmm, second. Can you see it? Okay, so where is it? Okay, yeah, that's fine. So we have copied the value, right? So let's change it. It's this value. So let's check the value. Uh, so it's quite similar, as I would say. And then let's say this thing. Uh, so this is how they mess with the shell. And then let us suppose this one for the previous one. This image one. Okay, let's just import again using OpenCV, right? So now let's make an image three. mm, F. Yeah. So now let's generate it. mm, this is a PCR. Instead of using NumPy, you can also use S area as well. Instead of like NumPy as area, you can just use it as this one. Mm, this is three, right? Mhm. Okay, and then what you do? Okay, this since this one is, I have to check this thing. But for now, let's just use NumPy as area, and then let's just print yeah. It should be the same. It should print out the same pixels. Ah. 236 244 191. Where's the thing? See? Where is it? See? You can see that, what do you say? What do you call it? I mean, 236, like 236 is now shifted to here. But the values are the same. Let's check. So let's see. Is it? Uh, if I, okay, I did not show it here. Okay. So you can see that it is showing the color of, what do you say? Uh, like the quote. It is showing the quote color. So now we know that it runs in this way. But in yesterday's, we learned about the thing. What is that thing called? Uh, yeah, the checker one. So we want to check like if the pixel values are similar, extra. So we will be testing that up. Here you can see that I've saved two pixels, checker A PNG and checker B PNG. So basically, I just crop those out. So now let's say, I mean, we have already imported those things. So sector A. Where is it? How is it stored as? It is stored as checker. No, yeah. Checker B. Let's store this as well. It should be in checker. No? Okay. And then what we want to do is what should we do? What should we do is okay, we want the pixel, right? We want to have the pixel. So okay, let's convert that into pixels. Then let's say pixel A equal to pixel A equal to we don't has a circle pixel B equal to F dot S a and then mm, let's so since like the different lighting can be like for that optical illusion, they made it so that it looks a bit different, but it is also similar. Like for in terms of how should I say the pixels, right? So let us check for the mean values. Like let's check the mean value. Like you can somewhat change the RGB channels in such a way that yeah it's it looks a bit different, but you get like you know how like you can change it so that it can be of similar color. So even if like let's say this tree can be changed in such a way that this can be improved to 237 and then this can be reduced to by like 40 and this can be improved to so that it can look similar but not really similar. So we for that one we really want to go for like the mean, like the average value, right? So let's say mm, to we want the mean value, right? Uh, let's take the mean. Mm, so in order to take the mean value, yes, we have already converted it to as error. And so what I just need to do is Excel. I need to test up this one. So I can just use this function. Uh, I want them to be printed in such a way that I can visualize it properly. So for instance, I want it to be in the y-axis, I mean along the horizontal. So let's say pixel P, V, and B of mean, axis. I want the axis to be similar. I'll get to it now. Okay, so it should print out, but okay. Okay. Instead of writing it like this, I think it's better if we write like if we can just make it print. Yeah, I think it's better if we just make it print. This then would be much better. Let's say, and then we should make it a little bit, yeah, meaning, right? Yeah, static. Yeah, yeah, I think we should just make it like this actually. Mhm. Okay. Marriage. Okay. Why is it not showing this thing? Okay. This one done. What? Okay. Okay. Yeah. Ah, so we can see that for Mine, it's similar. Like it's not like similar, but you get the point. Like you have some slight variation, but you can see that checker A and checker B, those two PNC. I cropped it, and so those two have similar like values. So you can say that the optical illusion will not technically be affecting to the like how image is being seen by the PC. So yeah, you can see like there are many ways of image analysis. So for now, we'll stop here. We have went through some many like some Python libraries, etc., etc. Yeah, for day two, it will be mainly towards OpenCV. So yeah, you will learn more about modules over there, etc., etc. So yeah, it's fine. It's chill. Uh, so for today, we'll stop here. Yeah, I know you guys must be tired as well regarding what we have been doing. Like day zero and day one on the same day. What? Like yeah. So yeah. So hope you guys enjoyed and hope you guys learned something. Yeah, anything like whatever. So yeah, we'll see you on the next class. The next tomorrow will be taken by different mentors. So yeah, we'll see once we start the project. So